Our last section of new material is 8.4, de Moivre's theorem. It's our power rule. Now, we talked about in 8.3, we talked about how addition pairs with multiplication and division pairs with subtraction. Our power rule is finding a repeated product. So I'm doing repeated multiplication, basically. Think about exponents. We said that if we had x cubed times x squared, that's x to the fifth, because if I'm multiplying the base, I add the exponents. If I have x cubed divided by x squared, I get x to the first, or just x, because I am subtracting my exponents. But what if I have x cubed raised to the second power? Well, this is where my power rule for exponents comes in, and I end up multiplying those exponents so that I get x to the sixth. Well, what about my power rule for complex trig form? That's where I get de Moivre's theorem. So what I'm being asked to do here is raise this complex trig form to a power. So like I might have 5 CIS 50 cubed, or to the fourth power. Now, I've had students in the past who say, well, couldn't I just put it in rectangular form and FOIL that out? Well, absolutely. But what you're looking at then would be something like, and I'm just making something up, but let's say 2 plus 3i to the third power. So I'm going to FOIL this, and then I'm going to multiply it by itself again. That would be handy enough. We could do that. We could handle that. But what if I have it to the fifth power or the seventh power? That is just too cumbersome and takes too long. We need a quicker way to get there. Our quicker way to get there is de Moivre's theorem. It says that if I'm taking a trig form of a complex number and raising it to a power, what I do is raise the modulus to that power and then multiply the exponent times the argument. So instead of adding or subtracting in here, I am multiplying the exponent to that argument value. This is my general form, my kind of expanded form. If I use my condensed CIS theta form, this would be r to the n times CIS of n theta. Now notice, to use de Moivre's theorem, we must be in trig form. We must be in trig form. Okay, so let's work through some of this. We're going to find this complex number raised to the fifth power and express the result in rectangular form. Let's think about our forms here. This is given to me in rectangular form. It's not CIS theta. So this is rectangular form. I need to answer in rectangular form, but de Moivre's theorem has to be done in trig form. So I'm starting in rectangular form, just a plus bi. My first step is going to be to find the trig form. Then I'll apply my theorem, and then I'll turn it back into rectangular form. Okay, how do I change rectangular form to trig form? There's just 3 short steps for that. The first one is to sketch. If I sketch this, A and B are both positive, so I'm in quadrant 1. My A is my real part. It's on the x-axis. My B, or my imaginary part, is on the y-axis. And I need R. R is the square root of both of those, the sum of the squares of those values. So R is the square root of 4, or 2. And then, because my trig form is CIS theta, I've got R, now I need theta. I need to find theta using tangent. Tangent is y over x. In this case, y and x are the same thing. My tangent is 1. What is the angle in quadrant 1 that has a tangent value of 1? Well, that angle is 45 degrees. I haven't been told whether to use degrees or radians. It doesn't really matter, because I am going to answer finally in rectangular form, so I can work with degrees or radians to get there. We're going to leave it in degrees because that's what we're mostly familiar with. So we have r CIS theta, which would be 2 CIS 45 degrees, and I want to raise that to the 5th power. There is my trig form for this problem. Now that I've got it in trig form, I want to apply de Moivre's theorem. Which is my power rule, basically, for trig form, complex numbers. So we're going to apply de Moivre's theorem. To do that, I'm going to start by writing this out in expanded form as I apply de Moivre's. So de Moivre's theorem says I raise r to that power, and then I multiply that exponent times the argument. So I have cosine of 45 degrees times 5 plus I sine of, and you can write, because multiplication, order doesn't matter, it's commutative. 45 degrees times 5 is the same thing as 5 times 45 degrees. 2 to the 5th power is 32. And then I have cosine 45 times 5 is 225 degrees plus I sine of 225 degrees. And finally, I need to go back because it says that it wants my result in rectangular form. This is that trig form raised to the 5th power, but I need my result in rectangular form. Because that's what I was told to answer, how I was told to answer. So I'm going to find the value for 225 degrees. 225 is in quadrant 3. It's my 45 degree reference angle in quadrant 3. So I have negative square root 2 over 2 plus I times a negative square root 2 over 2. And I distribute that 32 inside. So I have a negative 16 square root 2 minus 16I square root 2. Watch where you put your I for your imaginary number. All right, that's our steps. Let's go ahead and turn to the next page and practice it one more time. I want to encourage you to pause the video again, refer back to the example we just did, work yours out, and then restart your video. Okay, I'm going to walk you through a little bit of this. I found the trig form of my value by sketching my angle into quadrant 1 because both A and B are positive, finding R and finding theta so that I have 2 CIS 60 degrees to the 8th power. Now I'm going to use de Moivre's theorem. De Moivre's theorem tells me to raise R to the exponent, and then I do CIS of the argument times that power. So what that gives me is going to be 256 cosine of 480 plus I sine of 480. That's my trig form of my product. Well, what are my values for 480? Because I need to go ahead and turn that into rectangular form. 480 is coterminal. It's one full rotation plus 120 degrees. It's coterminal with 120 degrees. So I'm going to use my cosine and sine function values for 120. So I have 256, and then at 120, cosine is a negative 1/2. Sine is square root 3 over 2. So in rectangular form, this complex number raised to the 8th power is a negative 128 plus 128I square root 3. And you see that's a lot faster than writing that out 8 times and foiling it, or squaring it 4 times and then multiplying those 4 together. Either way, that would be a lot more work than using de Moivre's. Okay, what about roots of complex numbers? This is that inverse. Instead of squaring something, we take the square root. Instead of cubing something, taking the cube root. Instead of raising something to the 8th power, it would be taking the 8th root. Now, we are used to every number having either an odd or positive and negative, square root, 4th root, or just a single cube root. But we're just always used to considering real numbers. If we consider imaginary complex numbers, then every non-zero complex number has exactly n distinct or different complex nth roots. They're just not all real. They're just not all real. So if I want to take the cubed root of something, it's going to have 3 distinct cube roots, not just one. It's just that not all of them are real values. Some of them are imaginary. If I take the 5th root, I have 5 distinct roots. Now, when I say distinct, I mean different. Because when we're talking about angles, we have to consider angles of rotation. And we could keep just rotating around, landing in the same places, and getting repeated roots. But if I take the nth root, there will be that many distinct different roots. Okay, for a positive integer n, the complex number a plus bi is the nth root of the complex number x plus yi, if this is true. This gets us to our nth root theorem. So here's the important parts. We have, this defined the fact that n is going to be a positive integer. So our index is going to be a positive integer. We're taking the square root, the cube root, the 4th root, etc. We're not going to do the -2 root or the 1/3 root. We're not going to do anything fancy there. We're just going to keep that index a positive integer. Has exactly n distinct nth roots, because after that they start to repeat. After that they start to repeat. Here are your steps for your nth root theorem. First, you take the nth root of your modulus of r. Then you divide everything else by that value n. So this is what this looks like over here. They have it set up in degrees and radians. These are the same statements for both degrees and radians. If I'm trying to take the nth root of this complex number in trig form, that's the same thing as taking the nth root of r, right there, and then I take my argument and divide it by n, whatever that index is, and I take my rotation, my period, and divide it by n as well. If I'm in radians, that period is not 360, it's 2 pi. Okay, let's look at an example. This is where we start putting together our polar coordinate graphing with some of our algorithms and our problem solving. Okay, find the 3 cube roots of -8 and write the roots in rectangular form. Well, if I ask you for the cube root of -8, what would you tell me? Well, you would tell me -2, right? If I ask you for the cube root of -8, you would tell me that it's -2. And that's true. That's a true statement. Cube root of -8 is -2. That's my real root. If I have one real root, then I must have 2 imaginary roots. And we've just never worried about them before. So we're going to find all 3 this time, and we're going to look to see where they would be placed on the graph. The first thing we're going to do to find all 3 of our cube roots of -8 is to write -8 in trig form. Remember, my trig form is that RCIS theta. -8 is not in that form, so I need to write it in my trig form. To get it in trig form, the first step is to sketch it. A plus bi is my general form. I don't have an I as part of -8, so -8 is my real part. My imaginary part is 0. -8 would be over here, correct? So my angle theta, therefore, is 180 degrees, or pi. I'm looking at my work, and it looks like I've worked in radians here, so we're going to write this down as pi. What would r be? Well, r is square root of those values, the sum of those values squared. which would just be that absolute value that I'm given, 8. R is 8, theta is pi. So negative 8 in trig form comes out to be 8 cosine pi plus I sine pi. Or, if I wanted to write it in shorthand, 8 cis pi. There is negative 8 trig form. Second step is going to be to apply my theorem. Now, I don't have a fancy name for my nth root theorem, like de Moivre's for my power theorem. Remember that I take the nth root of r. I'm finding cube roots, so I take the cube root of r, which is 8. And then I divide everything else by 3, by that index. Now, I've got pi. Cosine and sine are both periodic over 2 pi. So I have times cis pi plus 2 pi k, every rotation thereof, divided by 3. I'm interested in the values where k is 0, 1, and 2. Why did I pick these 3? Well, I'm always going to start where k is 0, and I'm finding the cube roots. Because it's the cube roots, there will be 3 of them. So I do 1, 2, 3, where k is 0, k is 1, k is 2. So let's start working this out. This doesn't simplify. I've got pi third plus 2 pi thirds k. R is, well, we can go ahead and rewrite it. So R is, cube root of 8 is 2. And then I've got cis pi third plus 2 pi thirds, that's hard to read, I'm sorry, 2 pi thirds k. So now I've got to find, for k is 0, k is 1, k is 2. Now I could keep going, but they're just going to repeat, remember, because we would just keep going around and around the circle. What if k is 0? Well, if k is 0, this piece goes away, and I have 2 cis pi third. I have 2 cis pi third. What if k is 1? Well, if k is 1, I am adding pi third plus 2 pi third, which gets me 2 cis pi. Where k is 2, I'm going to add another 2 pi thirds to this pi. This was 3 pi thirds. If I add 2 more, I have 2 cis 5 pi thirds. Those are where my 3 roots fall. Now this is my trig form for those 3 distinct cube roots. I'm asked to give it in rectangular form. So I need to come up with that rectangular form. To find the rectangular form, I just plug in the cosine and sine function values of those different locations and multiply by the modulus, by 2. Now, before we find the rectangular forms, we're going to go ahead and start and graphically look at these 3 roots. Graphically, my nth roots are always going to be equally distributed around the circle. How far apart they are is determined right here. This tells you where to start, and this tells you how far apart they fall. We know that we have one real root at -2, correct? We have one real root at -2. So that one's going to be right here at -2. -2 pi, in fact, my polar coordinate form. But the first root falls at pi third. Pi third is 60 degrees, right? So where my modulus is 2, I'm at pi third. Then over here I've got -2 pi. And then down here, oh, that's not going to be a -2 pi. That's going to be 2 pi because I go over to pi and then out to 2. Sorry, that's at -2 on my, if I'm looking at rectangular, sorry. That's 2 pi. And then where's my third one? Well, I rotated 2 pi here, 2 pi thirds to get here. I'm gonna rotate another 2 pi thirds to get my third root. They are evenly distributed. So that one is at 2 5 pi thirds. They're graphically evenly distributed around my circle. My circle is, it's easier to think about things in degrees, right? So I'm going to say my circle is 360 degrees. I'm dividing it amongst 3 roots, which means I have a root every 120 degrees. I find another root every 120 degrees. I start at the first root. The first root is at pi third. I rotate 2 pi thirds, which is 120 degrees, to get to the next root. I rotate 2 pi thirds, which is 120 degrees, to get to the next root. And I could just keep rotating 120 degrees each time and find another root, but they're not going to be distinct. They're going to be coterminal with one of those 3 roots. Okay, let's go back over here and let's turn our trig form into rectangular form. To do that, I have to know the cosine and sine function values at pi third. Well, at pi third, cosine is 1/2 and sine is square root 3 over 2. What about at pi? At pi, cosine is -1 and sine is 0. What about at 5 pi thirds? At 5 pi thirds, cosine is a positive 1/2 and sine is a negative square root 3 over 2. So let's put those together and simplify them. 2 times 1/2 is 1. 2 times I square root 3 over 2 gives me I square root 3. That's the rectangular form of this first root. Trig form, rectangular form. What about the rectangular form for the second root? Well, that's my real one, -2. What about the rectangular form for the third root? That comes in at 1 minus I square root 3. So we have our 2 imaginary roots and our real root in rectangular form, because that's what I was asked to find. Trig form here, rectangular form there. Either one represents my 3 cube roots, 3 distinct cube roots. Let's do another one, because this is a new concept. We're going to find the 2 square roots of 4i. Well, how do I know there are 2? Because they're the same number of roots, distinct roots, as the index. How far apart will those 2 roots be? Well, 360 divided by 2 means those 2 roots are going to be, because I have 2 square roots, they're going to be, they will be 180 degrees apart. So once I know where the first one is, I rotate 180 degrees to get to the next one. We're going to walk through the same set of steps as we did in the last problem. We're given an rectangular form. We need trig form. So that's our first step, to write 4i in trig form. And then we're going to apply that root theorem. In trig form, I need to start by sketching where that would be. Well, this is my imaginary part, so my real part is 0. The imaginary part is a positive 4. So there's my angle. We're going to use theta is pi half. We're going to go ahead and stick with radians again. What would r be? Well, r is going to be the square root of 4 squared, so r is just 4. Remember that idea of modulus being the absolute value. In the first problem, I had just -8. The absolute value of that is 8. In this problem, I have just 4. The absolute value of that is 4. So in trig form, 4i looks like 4 cis pi half, trig form. Now we're going to apply our root theorem. So the nth root theorem. I'm going to take the square root. So I take the square root of 4, and then in here, I'm going to do cis of pi half plus 2 pi k divided by 2 because I divide by the index. Well, what does that turn out to be? This turns out to be 2 because the square root of 4 is 2. And then this piece would be CIS, half of pi half is pi fourth, plus 2 pi k divided by 2 is just pi k. And how many roots am I going to find? Well, I'm finding the square root, so there's just 2 of them. So we need k equals 0 and k equals 1. This is what I'm working with right here. All right, let's go back over and get the trig form that we're going to then need to put in rectangular form. So the trig form, where k is 0, I have just this, 2 CIS pi fourth. Now we already said we've got 2 of them because we're finding square roots. If I were finding the 5th roots, I would have 5 of them. But I've just got 2 because they're square roots. They're evenly distributed around my circle, so they're going to be 180 degrees or pi radians apart. The first root falls at pi fourth. The other root is going to fall rotation of 180 degrees or pi radians away from that. So when k is 1, my second root is at pi fourth plus pi. So 2 CIS 5 pi fourths. And that's my trig form of those 2 square roots. Okay, let's think about where those would fall on my circle. If I graph those, I would graph them at pi fourth is going to be right here. So that is going to be 2 pi fourth for polar coordinates. And then the other one is 180 or pi radians apart. So directly opposite that, I have 2 5 pi fourths. Remember when you are graphing polar coordinates, sorry guys, you always do the angle first and then you go out the units. So that would be 2 pi fourth and 2 5 pi fourth, where those 2 square roots fall. All right, let's change from our trig form to our rectangular form because that's what we're asked to answer in. Okay, so as we change this from trig form to rectangular form, I'm finding the cosine and sine function values at pi fourth first. So I have 2 times square root 2 over 2 plus I square root 2 over 2 because those are my values at pi fourth. And then for the other root, I find the values at 5 pi fourth. Well, 5 pi fourth is down here in quadrant 3, so both of those are negative. Make sure you watch your signs on these. When I distribute my modulus, I get square root 2 plus I square root 2. And then the second one comes out to be negative square root 2 minus I square root 2. And you're going to notice that when I have my sets of roots, I'm always going to see patterns like that. Because they're going to be evenly distributed, I will be using the same set of values. Okay, let's do a couple more examples together, because this one is definitely a little bit new. It looks a little different than the things we have done coming up, although really we're just putting together skills that you've already learned. Okay, this time we're finding the 4th roots. So 4th roots, how many of them are there going to be? Well, 4th roots means I'm going to have 4 of them. We're going to be working this one in degrees just because I said we were. We worked in radians, we practiced for these 2. We're going to go ahead and do degrees on both of these. 4th roots, if they are equally distributed around my circle, how far apart are they? Well, 360 divided by 4 means they're going to be 90 degrees apart. Once I know where the first one falls, then to find the other 3, I just rotate 90 degrees, 90 degrees, 90 degrees. We are given rectangular form, but to use our Nth Root Theorem, we have to put that in trig form. So that's my first step. So I sketch my value. Negative and negative means I'm down here in quadrant 3. The real number is a negative 128. The imaginary part is negative 128 square root 3. So this gets, I guess, a little bit more interesting because you have to square both of those when we're finding r. Find the sum of the squares of both of those. So to find r, we have square root of negative 128 squared plus a negative 128 square root 3 squared. Now when I do that, I do square root 3 squared is just 3. So I'll take 128, square it, and then multiply it by 3. And then I will add to that the square of 128. What this comes out to be is 256 as my value for r. Now let's look at tangent theta to see exactly what angle we're using down here. Well, tangent is y over x, so negative 128 square root 3 over negative 128 means my tangent function value is square root 3, and I'm in quadrant 3. If I look at my unit circle and do a little bit of calculation, figuring out which angle, I know it's not the 45 degree angle in quadrant 3. It's got to be either the 30 or the 60 reference angle in quadrant 3. So it's either going to be 210 or 240. And I check the tangent function values for both of those. I see that my angle I'm interested in is 240 degrees. So I know my trig form. My trig form is 256 CIS 240 degrees. Now I need to apply the nth root theorem. So if I'm finding the fourth root, I take the fourth root of r and I divide every rotation of that. So that would be 360k, all of that divided by 4. So what am I working with? I'm working with the fourth root of 256 is 4. And then I've got CIS, 240 divided by 4 is 60 degrees. So that's the location of my first root, plus 90 degrees K, which we already knew every root was going to come at a rotation of 90 degrees after the first root. And I need values of K, 0, 1, 2, and 3. How do I know where to stop? Well, how many roots do I need? This case I need 4 because I'm finding the fourth roots. So 1, 2, 3, 4. All right, let's go through and find the trig form, and then I have to change that to the rectangular form. At the same time, we are going to be graphing them over here. We know that our first root, where k equals 0, for k equals 0, we've got this first value, 4 CIS 60 degrees. So my first root is at 60 degrees, right there. And that polar location is going to be 60 degrees. Well, where's my next root going to be? My next root, I'm going to add 90. So I get 4 CIS 150. And then my third root is at 4 CIS add 90 again. And I'm at 240. And then my last of the fourth roots is at 4 CIS 330 because I add 90 again. So when I'm rotating around my circle, putting them on my polar coordinates, I add 90, add 90, add 90. Since I'm adding 90, that gets me to 180. I'm going to go ahead and I can draw these straight across. So I've got 60, I've got 150, and I've got 330. Oh, that's supposed to be a straight line. Didn't do very good about that. So I've got 460. I have 150 as that polar coordinate. I have 240. And I have 330 degrees. And these are 1, 2, 3, 4 units out, 4 units out, 4 units out, 4 units out. Okay, so that's what it looks like on a graph. That's what it looks like graphically if I were going to put it on the circle, graphing polar coordinates. I never mess with trying to do the bullseye because I can't draw those circles, those concentric circles. They just come out ugly. This is my trig form of my 4 fourth roots, but I'm told to answer in rectangular form, so I need to do that. I need to go ahead and plug in the cosine and sine function values of each of these and simplify. So this first one is 4 times 1/2 plus I square root 3 over 2. The next one, I'm using the reciprocal of that. Well, not reciprocal. I'm just going to hush and write them down. For the next one at 150, I'm in quadrant 2. For the third root, I'm in quadrant 3, so they're both negative. And for the last one, I'm in quadrant 4, so my cosine value is positive and my sine value is negative. Where am I finding these values? Where I'm either remembering them, I'm finding them on my notes because I have a key to refer to. But you are either remembering what they are for these special angles or you're referencing your unit circle. And then I simplify by distributing in the 4 so that I get these values in rectangular form, which is what I was asked for. This first one comes out to be 2 plus 2i square root 3. The second root at 150 degrees in rectangular form is negative 2 square root 3 plus 2i. The third root at 240 degrees is negative 2 minus 2i square root 3. And then my fourth root at 330 degrees is at 2 square root 3 minus 2i. Notice the positive and negative values reflect which quadrant they're in. And I have that repetitive pattern that forms as I rotate around the circle. All right, this next one, I usually skip when we're in class because we don't have time to go through all of the examples, and I want to do the 2 on the next page. What I'm going to do for you is I'm just going to show you my key so that you can see what that answer would be. Go ahead and pause the video, do yours, come back to it and look at it if you want, whatever you want to do. As you can see, I have it marked skip because it's just another fourth root problem, which means you have a root every 90 degrees again. But that's what those results would be. So you have another example in your notes. Okay, let's do this final page of notes now. So example 4, this time we're solving equations. This isn't any different really than what we've been doing, I promise, because we're going to be solving by taking the nth root. In fact, this is actually easier because it does not instruct us to give it as rectangular form. It instructs us to graph them as vectors in the complex plane. We've already been doing that. On the last several examples we did, we found the trig form, we found the rectangular form, and we graphed them as vectors in the complex plane. So this time you don't have to find the rectangular form. You just have to identify the trig form and then put it on the polar graph. Okay, so let's look at this. We have the equation x to the 5th minus 1 equals 0. Well, that means that x to the 5th is equal to 1. So my solution set are going to be the 5th roots of 1. X is going to be the 5th root of 1. Now, traditionally, we would say, oh, the root of 1 is 1, right? Well, yeah, the real root of 1 is 1, but I have one real root and then I have those complex roots. So how often am I going to have a root when I have 5 of them? Well, if I have 5 roots, 360 divided by 5 means I'm going to have a root every 72 degrees. So we're not looking at special angle values, right? If they're going to be every 72 degrees, they're not going to fall on our nice unit circle special angles, which means if I did need the rectangular form, I would be finding calculator approximations. Okay, so we know, well, we don't know. We need to find our trig form of 1. Well, if my value is 1, that's real and that's positive, so that's 1 right there. So I can use 0 degrees. So I can say that I'm taking the 5th root of 1 times CIS, 0 degrees divided by 5 plus 360K divided by 5, which simplifies to be, well, the fifth root of 1 is just 1. And then I have CIS 0 degrees plus 72K, however far I need to go. We need the first 5 roots because those are going to be our 5 distinct roots. So we're going to be finding K equals 0, 1, 2, 3, and 4. Let's just list that out. K equals 0, 1, 2, 3, and 4. And I'll get up there so you can see everything. Okay, well, what's my starting place? 1, CIS 0 degrees. Now, yeah, R is 1. You don't absolutely have to write that there, but just so we don't forget our R CIS theta form, I'm going to go ahead and write it. So my first root is at 0. Where's the next root? Well, how often? Every 72 degrees. So that's going to be at 72. My third root, I will add 72 there and get 144. I add 72 again, and I get 216. I add 72 again, and I get 288. Now, these are our values that we need to put on our graph. It's hard to rotate to show equal rotation of 72 degrees when you've got 5 roots because none of them is going to be directly opposite any of the others. It kind of looks like spokes on a wheel. I have a hard time doing a good job of that, but we're going to do our best. So we've got our first root at 0. So this would be, this would be 1, 0. And then we've got 72, I'm going to put right about there. So that's going to be 172. And then we've got 144. I think I'm going to go with right about there. So 144. And then we have 216, which ish, maybe about there. 1, 216. And then our fifth root is 1, 288. Okay, that doesn't look bad. So there is a graphical representation in the complex plane. Now, we gave polar coordinates because we are in our complex plane. All right, let's do this last one. When I solve, I look at a solution for this equation. I would have x to the 6th equals negative I. And then to finish solving, I will take the 6th root. Since I'm finding the 6th root, how often will they come? Well, 360 divided by 6 comes out to be 60 degrees. So I'm going to have a root every 60 degrees. We need to know our trig form to start with. Negative I, the real part would be 0. The imaginary part would be negative 1. So that's my angle theta. Theta is 270 degrees. It's easy when they're quadrantal like that. R is going to be that modulus. It's going to be the absolute value. Square root of 0 squared plus negative 1 squared ends up to be 1. R is 1 again. So I have 1 CIS 270 degrees. And then what I need to do is find the 6th root of that. So I'm going to be taking the 6th root of 1. I'm going to be dividing that by 6 and saying plus 360k divided by 6. And that gives us 1. 6th root of 1 is 1. CIS. Well, what is 270 divided by 6? It's 45 degrees. So this one's going to be easy. Plus 60 degrees K. And I'm finding 6 values. So I'm going to be finding from K is 0 to K is 5. So we have K equals 0, 1, 2, 3, 4, and 5, because that gives me my 6 distinct roots. Now, if I want to go over and look at the graph before I put them in trig form, I can absolutely do that. My first one is at 45 degrees, so that's easy. So I've got 45 degrees as my polar coordinates. Where's the next one? So the first one is at CIS 45 degrees. I could write that 1 there. I don't have to. Every 60 degrees. So the second one is at CIS 105. Add 60 again. CIS 165. Then I end up at 225. 285, and 345. And let's see if we can rotate those around. They're an even number of roots, so they are going to be directly opposite each other. So that's nice. I noticed that this k equals 3 comes out to be 225, and that one is directly opposite my 45. 105 would be right here, about here. And what root is directly opposite that? Well, 285. 285. This one's going to be 105. That's 180 degrees apart. This next root, I've got 45, 105, and then 165, which is not quite to 180, and then I'll have the one opposite it. So I've got 165 degrees, and then 165 plus 180 gets me around here to this 345. Oh, I didn't add this one in. 225 degrees. So that gives me 1, 2, 3, 4, 5, 6 distinct sixth roots. I could just keep rotating and get more, but they would just land on top of the roots I've already been given.